Good morning, everybody. During the last lecture, we have discussed the electric charge and the attractive and repulsive forces between electric charges. And today we will continue with electric field and electric dipoles. Here you see two balls. On the left side, we have a bigger ball with the name of A ball, and it is positively charged. And on the right side, we have a test charge, Q0. This test charge is also positively charged, okay? Then what about the forces on this positively charged balls? You see that this test charge applies this force along the negative x direction with minus F0, okay? And this ball applies this force with the same magnitude but opposite direction, because this force is repulsive here, okay? They repel each other, and then in magnitude these forces are equal, but they are in opposite directions. So now just remove this ball on the right side. So here we have a ball on the right side. This is test charge with the charge of Q0, okay? And if I put this ball here, this ball feels a force, okay? A force acting on this test charge due to this bigger ball here on the left side. What is the reason for this force? Why this test charge feels a force acting on it, okay? So just remove this test charge from this point and just put here a point, okay, in order to show the position of the test charge. Here now there is no charge, but I just put a sign to show the position of the test charge. So now we can say that body A here on the left side somehow modifies the properties of space at point T. So if here on the left side I have a positively charged particle or ball, it modifies the properties of space around itself. So it modifies the space here, it modifies this P point, it modifies this P point, it modifies this P point, okay? So each charge, whether negatively charged or positively charged, changes or modifies the properties of the space around itself, okay? So then there should be something here due to the A ball, and this is the electric field produced by A ball, okay? So here we have A ball positively charged, and around itself at any point it modifies the properties of the space. So if I put here a test charge with Q0, then due to the electric field of the A ball produced by the A ball, this test charge will feel this F force, F0, okay? And this electric field is given with this expression, okay? Electric field is given with F over Q. Here, be careful. Here we have E, this electric field produced by A ball, and this is the F0 acting on this test charge, and this Q0 is the charge of the test charge, okay? You can remember the formula Lorentz force from your high school years. Remember this formula, Lorentz force is given with this expression, Q times E plus Q times V times B. This is cross product, okay? Here there is no magnetic field and we are not dealing with this component of the Lorentz force, but look at this one, okay? If you take the force from this equation, you will get this one. You see, you already know this information from your high school years, okay? This is the electric field at point P due to the A ball. So now let's continue with the electric force produced by an electric field. So electric force is this one, and it is produced by electric field. Okay. Electric field produces an electric force. So again, here on the left side, we have Q ball, or we have A ball with the charge of capital Q. And on the right side, we have test charge with the charge of Q0. And it is also positively charged. And due to charge capital Q, we have electric field. It is along the positive X, let's say. Okay. And then this force is also along the positive X. And this force, electric force, due to the electric field, is given with this expression. Okay? But what happens if we have a negative charge? Here we have positive charge, but here we have negative charge with the blue color. And this capital Q is same. This positively charged A ball produces this electric field, okay, again along the positive X. But when the test charge is negatively charged, the direction of the force is opposite to the direction of the electric field. You can understand like this. Just put this one here, okay, just write this equation. Here we have positive charge of the test charge, but here we have negative charge of the test charge. Then the force here is opposite to the electric field. Do you have any question here? Then let me continue. Here we have a point in space. The name of the point is S. And here we have another point, another position. The name is P. And here in S point, in S position, we have Q charge. And here on the right side at P point, we have test charge with Q0. And the distance between these two charges is given with R. Okay, this is the distance in between. And this is the unit vector. This R vector is the unit vector, points from source point to field point P. So what we mean with source point and field point? Source point means that here we have, for example, positively charged ball, okay, at S point here. And here we have another positively charged test charge. And this is called a source of electric field. This is called a source of electric field. This positively charged ball produces electric field at P point, okay? Actually, it produces electric field around itself, every point in space. But now we are dealing with the electric field at P point. So then, if this source, this charged ball at point S is positively charged, then electric field will be in this direction from source to the space. Okay, this is the direction of the electric field, you see. And at P point here, we have this electric field due to the source charged particle. Okay, so and here we have the definition. An isolated positive point charge Q points directly away from the charge in the same direction. So this positively charged particle produces an electric field, and its direction points directly away from the charge in the same direction as this unit vector. Okay, so look at the direction of the unit vector and look at the direction of the electric field. So I would like to express this one. If you have a positive charge, then the electric field, the direction of the electric field is from source to the space. Okay. So now let's calculate the magnitude of this electric field. During the last lecture, we have given this force, the attractive or repulsive electrostatic force between two charges, okay? This is given by the Coulomb's law. And here what we have, this is the K, you remember, constant. And you can also write this one in this form, K times Q times Q0 over R squared, distance in between. This is constant, and it can be written like this, okay? This is electric constant, epsilon 0. So, okay, we have already given this information during the last lecture. Now, just use the formula for the electric field. Electric field is given with force over Q0, okay? Here we have a positively charged particle at S point, and here we have P point, and here we have a test charge. And due to this positive charge at S point, we have electric field or repulsive force. This is given with F0, and here we have distance R, okay? Then electric force is given with this expression, electric field is given with this expression. If you divide this F0 by Q0, then you can get expression for the electric field at P point here. I would like to remind you that if I calculate the electric field at this point, let's say this is another point called a C, the electric field produced by this source will be completely different. If you choose this point, and if you have a charge here, the electric force and electric field at this point completely will be different because distance changes, okay? So electric field depends on the distance, square of the distance. So here we have Q. What is this Q? This is the charge of the source, okay? Don't forget, Q is the charge of the source. So then we have electric field depends on the distance from point charge. Okay, now let's discuss the direction of the electric field for the point charges. Here we have a point charge, or you can say source, okay? It is positively charged, and I choose different points in space, okay? For example, also here. So this point charge produces electric fields around itself in space, and the direction of the electric field points away from the charge, okay? The direction of the electric field at any point around this point charge points away from the charge, okay? So this is the direction of the electric field at any point. Okay, now let's continue with the negative charge. Here we have negative point charge. And what about the direction of the electric field? So this negative point charge produces electric field around itself in space, and the direction of the electric field at any point points toward the charge from space to the charge. This is the direction of the electric field produced by this point charge. And what about the magnitude of the electric field? So here, let's say we have another point, and here we have electric field. Let's say this is E1, and here we have another point, and we have electric field E2. What about the magnitude of these electric fields? Are they same or different? Of course, they are completely different in magnitude because the electric field produced by this point charge depends on the charge of the source. Okay, charge of the source is constant Q, but what about the distance from the source? The distance for this point to the source is R1, but for this point, the distance to the charge is given with R2. So what do you see here? R1 is much bigger than R2. Then the electric field will change depending on the distance from the source. Do you have any question here? Okay, now I would like to give you another important information from the book. Maybe you already know this information, but it is very useful when you are dealing with the problems related to this chapter and also for the forthcoming chapters. In some situations, the magnitude and direction of the electric field and hence its vector components have the same values everywhere throughout a certain region. We then say that the field is uniform in this region. An important example of this is the electric field inside a conductor. Okay, so if this is conducting sphere, for example, within this metal, everywhere, electric field is uniform and zero. Okay, don't forget this one. Let me also continue with this sentence. If there is an electric field within a conductor, the field exerts a force on every charge in the conductor, giving the free charges a net motion. By definition, an electrostatic situation is one in which the charges have no net motion. We conclude that, this is very important, this one. We conclude that in electrostatics, the electric field at every point within the material of a conductor must be zero, okay? Don't forget this one. This is very important. If you have a metal and it is completely filled with the metal, within this metal, electric field is zero, okay? Electric field at every point within the material of a conductor must be zero. But let's consider you have a metal sphere, okay? And you have hollow within the sphere. So in this part, you have metal, okay? But in the center, you have a hollow, okay? An empty part. So electric field in this center can be different from zero, okay? So depending on the conditions. So not that we are not saying that the field is necessarily zero in a hole inside a conductor. This is completely field conductor. This is completely field conductor. But here we have conductor, but we have a hole within the conductor. And electric field can be different from zero within the hole inside a conductor. Do you have any question related to this statement? Then let me continue with the bio application, sharks and the sixth sense. Here you see a shark. I would like to magnify the picture. Can you see these points on the skin of the shark? There are many points on the surface of this shark. So what about the duty or property of these points? Sharks have the ability to locate prey that are completely hidden beneath the sand at the bottom of the ocean. So this shark can find its prey. Okay, so how this shark can do that? They do this by sensing the weak electric fields produced by muscle contraction in their prey. So here, just consider we have a smaller fish. This is prey. Okay, and this shark would like to eat this one. Okay, so due to these muscle contractions, this prey produces electric field around itself. Okay, then this shark can detect these electric fields by using these points on its skin. Let me clean this part. So how it could be possible? Sharks derive their sensitivity to electric fields. It is also called a sixth sense, altıncı his, from jelly-filled canals in their bodies. So here there are canals. Let me draw from this side. So now just concentrate on this one. I am looking this part, okay? This is a shark. So here there are canals, many canals, okay, in different directions. And these canals filled with jelly material, okay? And these canals end in pores on the shark skin. So here we have pores, okay? I have shown you. Let me show you again, then you will better understand. So you see there are pores here, but actually these are entrance of the canals, okay? So here we have many canals, okay, enters into the shark beneath the surface. So an electric field as weak as 5 times 10 to minus 7 Newton per coulomb causes charge flow within the canals and triggers a signal in the shark's nervous system. So if there is an electric field here, if there is an electric field, or let's say a source here, electric field source, these canals can detect these electric fields, okay? Then the nervous system of this shark can detect these electric fields. Because the shark has canals with different orientations, it can measure different components of the electric field vector and hence determine the direction of the field. So then sharks can find position of their prey, okay, by using these canals, these pores. Actually, here I'm talking about 2 bio application related to the electric fields. This fish produces electric fields. You can consider that this is an electric field source, okay? During the muscle contractions, it can do that. And this shark can detect these electric fields, and it can also detect the direction of the electric fields and then locate the position of the prey. Do you have any question related to this example? Let me continue. Example 21.7 from the book. This is electron in a uniform field. First of all, let me read the question and then let's continue. Here, within this example, you will also use your information from Physics 1. In Physics 1, we have learned constant acceleration. We have learned Newton's laws of motion, okay? So within this example, you can apply electric field, electricity, and Newton's laws in a single example, okay? You will use your old information. So it is very easy to understand, just concentrate. When the terminals of a battery are connected to the 2 parallel conducting plates with a small gap between them. Here we have a battery, this one, 100-volt battery. This is the positive pole, this is the minus pole, and here we have 2 parallel plates. So this is top one, negatively charged plate. It gets contact from the negative side of the battery, and here we have positive side of the plate. And here you see an electron with the blue color, okay? And there is an electric field within this parallel plate, and the direction of the electric field is from positive to the negative. You see, let me draw this one. This is very important. So here we have positive plate, and here we have negative plate, and look at the direction of the electric field from positive to the negative. This is the direction of the electric field, okay? Since we have electron here, electron is negatively charged, then here you see, you put the charge of the electron. The charge of the electron is given with the E. We have done it during the last lecture, okay? Then it has negative charge, minus E. Then what about the direction of the force? Direction of the force is opposite to the electric field because here we have a negative charge. This is the direction of the electric field. This is the direction of the force acting on the electron. Actually, here there is also a gravitational force acting on the electron, but as I discussed during the last lecture, since the mass of the electron is very, very, very small, then the gravitational force acting on this electron is very, very small compared to the electrostatic force, compared to the electric force, okay? So during the last lecture, we have compared the gravitational forces and electric forces in subatomic particles for electrons, for protons, for let's say quarks. We have for atoms, we have discussed this one. Electric force is much bigger. So here we will neglect the gravitational force, okay? So then let's have a look. What is the question? If the plates are 1 centimeter apart and are connected to a 100-volt battery, as shown in figure here, the field is vertically upward and has magnitude, this value, 1 times 10 to 4 Newton per Coulomb. This is the magnitude of the electric field. During the physics 1, I always insisted on the units, okay? You must be very careful with the units. Here, the unit of the electric field is given, but you can also produce this unit by yourself. So remember the formula for the electric field. This is the electric field formula, F over Q, right? What about the unit of the force? Newton, we have already learned in physics 1. And what about the unit of the Q? We have learned during the last lecture. It is given with Coulomb, okay? Then the unit of the electric field is Newton per Coulomb. And here, within the parallel plates, we have this electric field. And now question 1. If an electron with negative charge, minus 1.6 times 10 to minus 9 Coulomb, and mass with 9.11 times 10 to minus 31 kilogram is released from rest at the upper plate, what is its acceleration? So in physics 1, we have dealt with gravitational force. Just consider here we have a mass and only gravity acts on this mass, okay? Then if you release this mass from the rest, after a certain time, it will reach to the ground and it will have certain velocity. Here it has 0 velocity, okay? And here we have certain final velocity, okay? So we have solved many problems related to this example in physics 1. But here, our mass is very, very small. Look at the mass of the electron here in the question. Mass of the electron is 10 to minus 31 kilogram. 10 to minus 31 kilogram. Very small mass. Then this force will be very, very small compared to the electric force due to the electric field. Okay, then we will neglect this gravitational force. I have already discussed this one during the last lecture, but I wanted to repeat this one again. So now it is released from rest at the upper plate. What is its acceleration? Second question, what speed and kinetic energy does it acquire while traveling 1 centimeter to the lower plate? Speed and kinetic energy are asked. And the last question, how long does it take to travel this distance? Okay, so here we have 1 centimeter between the plates. And what about the time to travel through this distance? Okay, so then you can use constant acceleration formulas from chapter 2. Why? In order to use constant acceleration formulas, what do you need? Force must be constant, okay? If the force, remember this formula, if the force is constant, then acceleration is constant, and you can use constant acceleration formulas. What about the force here? The force is given with minus E times E, okay? or force here is given Q times E. What about the electric field? What about the charge? Charge is constant, charge of electron. What about the electric field? Between parallel plates, we consider a uniform electric field. Electric field is uniform here. In this point, in this point, in this point, in this point, electric field does not change. You can calculate this one, okay? Everywhere between the plates, electric field is constant, charge is constant. Then I have a constant force here. Then if F is constant, then acceleration is constant. Is this part clear? It is very important to understand the solution of this question. Okay, then let me continue. Here we have force. Just choose that this is the x-axis and this is the y-axis, and just choose that positive y is downward. Then I show force with Fy, and Fy is written with m times ay, okay? And then I can write this expression. This Fy is also given with minus E times E. This is the electric field. This is the charge of the electron. Then I have this expression. Electric field is given in the question. Charge of the electron is given in the question. Mass of the electron is given in the question. Then I can calculate acceleration of the electron. Okay, it is given with minus 1.76 times 10 to 15 meter per square second. This is the acceleration of the electron. And what about its velocity here? In order to calculate the velocity, I can use this expression for constant acceleration. Again, you can remember from the chapter 2 of the physics 1, Vy square is equal to V0 y square plus 2ay bracket y minus y0. This is the final position. This is the initial position. And for us, this one is 1 centimeter. And Vy0 is 0 because we release the electron from the rest. And y0 is also 0. And y is minus 1 centimeter. Then if you put everything here, then we can calculate the velocity of the electron. Look at the velocity of the electron, 5.9 times 10 to 6 meter per second. Very huge velocity. You see, speed is huge. I mean, from 1 centimeter, if you release this electron without any electric field, you can also calculate the gravitational force, and you can also calculate the velocity and acceleration. And you will see that it will be very, very small compared to this one and negligible. Under electric field, you can accelerate electrons up to very high velocities, very high energies. What about the kinetic energy of the electron? You can use this expression. Again, the information from the physics 1, 1/2 mv square. We know the mass of the electron. We know the velocity of the electron. We have already calculated, put it there. Then finally, you can calculate the kinetic energy of the electron in joule. And the last question, what is the time? How long does it take to travel this distance? What is the time? Look at the time. Result is very interesting. You can use this expression for the constant acceleration, again from the chapter 2. Vy is equal to V0y plus ay times time. Ay is acceleration. We have already calculated here. Just use this acceleration. And this is 0. We have also calculated final velocity. Put all numbers here. Then you will find the time 3.4 times 10 to minus 9 seconds, or nanoseconds. Okay, 10 to minus 9 seconds or 3.4 nanosecond. It is very short time. Okay, within nanoseconds, this electron can travel this distance under this electric field. So you can understand from this solution that for subatomic particles, for electrons, for protons, for other subatomic particles, the electric force is much bigger and produces much bigger effects compared to the gravitational force. Okay, do you have any question related to this example? Then let me continue with the superposition of electric fields. Up to now, we have discussed single electric field source. But what happens if we have different electric field sources? For example, here we have a positively charged Q1. It produces electric field around itself, okay, from source to the space. Okay. And here I have another Q2 charge. It is negatively charged. It also produces electric field around itself, but its direction from space to the charge, okay, because it is negative charge, right? Then I would like to calculate the electric field produced at this P point by these two charges. How to do that? So first of all, look at the first one. Here I have positive charge. It has certain R1 distance to the P point, and it produces electric field in this direction at this point. It is given with E1. Okay. And here I have another charge, which is negatively charged, Q2, and it has this distance to the P point. This distance is given with R2, let's say, and it produces electric field from P point to the source here, okay? Look at the direction. The direction of the electric field produced by Q1 is in this direction, and direction of the E2 is from P position to the Q2 source. Then, what about the superposition of these electric fields? Electric field is vector, okay? By using the vector components, you can calculate the resultant vector or vector sum of E1 and E2, okay? Then this is the electric field, total electric field, net electric field at P point, okay? So you can use the vectors. We have already discussed in Physics 1. What was the first chapter of the Physics 1? The first chapter of the Physics 1 was the vectors. And my old students remember that vectors are very important in physics, in science, and also other fields of engineering, okay? So addition of vectors, subtraction of vectors, scalar product, vector product, these are very important information. Like basic mathematics, vectors are very important. So even in physics too, you are using the vectors and you are using the superposition of the vectors. Okay, this is very important information. If you would like to be successful in physics too, you should always keep this information in mind. This is called as charge density. I will show you many examples in the forthcoming chapters, but here I would like to give you a short summary. Let me draw some different shapes here. Just consider that here we have a metal rod. It is very long, okay? It has certain length, very long rod. And then here I have a metal plate. It is very thin. You can consider more or less two-dimensional, okay? This is plate. We can say this is long rod. This is thin plate. You can consider that this is one-dimensional. You can consider this is two-dimensional. And just consider that here we have a sphere, metal sphere, and this is three-dimensional, okay? It has certain radius, and this has certain area, okay? So, depending on the shape of the object, depending on the shape of the metal, charge density changes, okay? If we have a long rod, we use linear charge density. And it has symbol of lambda, a Greek letter, lambda, okay? For long, thin, charged plastic rod, you can also consider, okay? It can be plastic, but it is charged, and it is long and thin, okay? Here I can write thin, long rod. Plastic, metal, it doesn't matter. And it has linear charge density. This one. If you have thin plastic sheet, or if you have thin metal sheet, but it is charged, then the charge is distributed over a surface. Let's consider that the charge is distributed uniformly on the surface. Then it has surface charge density, and it is shown by sigma symbol, okay? It has surface charge density. And if you have three-dimensional object, charged three-dimensional object, and if it is uniformly distributed, let's say, then we have volume charge density. Okay, and volume charge density is shown by rho symbol. Okay, and here, what about the unit? Unit of the linear charge density is given with coulomb per meter. So you can consider like this. Here I have one charge, 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 okay? And let's say each charge has certain Q charge, and it is given in coulomb, okay? So then the unit for the linear charge density is given with coulomb per meter. For the surface charge density, we are talking about charge per unit area, charge per unit area. For the volume charge density, we are talking about charge per volume, per unit volume, okay? So charge distribution, uniform charge distribution, non-uniform charge distribution in problems are very important terms, okay? You must be very careful. So we will mostly use these symbols and definitions in the problem solving of the questions within this chapter and also in the forthcoming chapters. Do you have any question related to this charge densities? Then let me continue with another example. Example 21.9, field of a ring of charge. Here we have a ring, you already see, like Smith, okay? And here we have P point, and I would like to calculate the electric field at P point produced by this charge ring, okay? Now let's read the question. Charge Q is uniformly distributed around a conducting ring of radius A. Radius of the ring is given. It is A. Find the electric field at a point P on the ring axis at a distance x from its center. So the distance from the center of the ring to the P point is given with x. So the question is, what is the electric field here? So how to solve this problem? In order to solve this kind of problems, you can use the integral, okay? You produce infinitesimal parts of the object, then calculate electric field of each part, then you can calculate finally the total electric field produced at P point. I will explain what I mean. Here, I choose a very small segment of the ring, and the length of this segment is ds. And charge of this segment is dq, okay? What about the total charge of this ring? The total charge of this ring is q, okay? But I'm dealing with very small segment here located at this position. It has certain very small ds, infinitesimal segment. And what about the distance of the s part to the p point? The distance can be calculated by using the geometry. This x is given, a is given, then I can calculate distance r with this expression. x square plus a square. Okay, then this is the dE, the electric field produced by a very small segment of the ring. If you understand this one, you can solve more or less every question related to this topic. And of course, it has x component and it has y component. Okay, I'm talking about this vector. And here we have alpha angle. Just choose another segment here, another ds segment with the same dq charge. Okay, then what about the electric field produced by the small segment here at P point? The charge of the P point is positive here, don't forget. You have another electric field component, okay? This is also dE, and it also has y component here, and it also has x component here. So you can see that from the vectors, these two components, y components, cancel each other, and we have vector sum of x components. Okay, you can also calculate this small segment here. Okay, here. So all of them will produce an electric field along the x direction, and along the y we will not have any electric field component. Okay, then finally we can calculate electric field at P point by using the integral. Okay, this is the idea. You can also do this one by using different shapes. For example, let's consider that you have a metal sphere here, and here you have P point. You can calculate the electric field produced by this sphere at P point. Just consider that you have a metal rod or plastic rod. This is charge, for example. And here I would like to calculate the electric field at P point. Okay, here we have many charges. If you separate this rod into the infinitesimal parts, okay, then you can calculate each component of the electric field produced by each segment of this rod. Or just consider the same rod, you can choose this point, okay? Each point has different distance from the rod to this point. Then using integral, again, you can calculate the electric field. But in this type of calculations, charge density information, which I have given here, is very useful. So if you have thin, long rod, you have to use lambda linear charge density. If you have thin metal or plastic charge sheet, you have to use sigma surface charge density. And if you have volume, charge volume, then you can use rho volume charge density. Now let's continue to the solution. Then the final electric field produced at P point will be along the x direction. Okay, it will be like this. There will be only x component of the final electric field. And as I told you, I will calculate dE, the electric field produced by each segment of this ring. Okay, then finally I will integrate this one over this total length. So then what about dE? Remember the electric field formula. Electric field formula is this one. 1 over 4 pi epsilon 0 q over r square, right? What about the charge of the source? Here, the charge of the source is dq. And instead of q, just use dq. What about the distance r? R is given here. Okay, just put this one here. Then we will have this expression. This is the electric field produced by very small segment of the ring here at this point. Then what about the x component of this field? This field is produced by dq charge by a very small segment of the ring, and it has x component, dex, and it has y component. Since the y components are cancelled with this ones, each segment cancels the y components, okay? Then we only have x component. For this reason, I will only deal with the x component. And in order to calculate the x component of this one, I can write this expression, dE times cosine alpha. Alpha is this angle. And I know this x, I know this a, then I can calculate the cosine alpha. Cosine alpha is x over r. Instead of r, I can write this expression, which is given here. You already know. Then here I have dEx, and here I have dE times cosine alpha. dE is given here, just put this one here, and cosine alpha is given here, this one, just put this one also here. Finally, I will have this expression. Here we have something is neve. We have dq, charge of the small segment. What is the charge of the small segment? The charge of the small segment is given with lambda times ds. This is the charge of the small segment. This is the linear charge density. This is the length of the segment. And this is the charge of this small segment. Okay, so then instead of dq, I just write lambda times, lambda is here, ds. ds is this one, length of the small segment. Okay, then I have dex. In order to calculate all contributions from the ring, then I can integrate system. What about this distance? This is the circumference. It is given with 2 pi a. A is the radius of this ring, okay? This is the circumference of the ring. Then I will integrate this one over ds. So just take this one, put this one here and integrate from 0 to 2 pi a, okay? X is constant. X is constant. Radius a is also constant, okay? Lambda linear charge density constant. X is constant. You can take all constant numbers out of the integral. Then on the right side, I have this one. Look at this integral. Integral from 0 to 2 pi a. This is the circumference of the ring, okay? Total length of the rod you can consider if you make it rod from this ring. Then this is the ds, okay? So then what about the result of this integral? Result of this integral is 2 pi a, okay? Then put this solution here, and then finally I have electric field along the x-axis. So where this q comes from? Here in this equation, there is no q. But how to get this q? Look at this one. This is the total length of the ring, okay? And this is the linear charge density. If you multiply linear charge density and also length of the ring, circumference of the ring, then you will calculate total charge of the ring. This is q. This upper one is the charge of the small segment. But this lower one is the total charge of the system. Then lambda times 2 pi a gives us this q. Then I can get electric field like this. Okay, so this is the solution. Here I have an evolution part. My old students know that I really like this evaluation parts within the examples and solutions of the problems within this book. So here we have very nice information. This equation, what about this equation? What it tells us shows that electric field is 0 at the center of the ring. here. When the x is 0, here we have x, you see? If you put x is 0, then electric field at the origin of this ring will be 0, right? This electric field will be 0. So just by using this equation, this solution, I can get this information. In addition to that, when the field point P, now I am dealing this P point, but if this P point is much farther from the ring than the ring's radius, so then we have this situation. So this is the x, this is the radius of the ring. But if point is here, now I have another point, and this is the x distance. And x distance is much bigger than the radius of the ring. Then what will happen? Look at this equation. Here I have x, and here I have x and a. If this x is much bigger than a, then this part of the equation will be like this. Let me do that like this. E is equal to 1 over 4 pi epsilon 0. I'm just writing this solution. Q times x. And here we have x squared plus a squared 3/2 I. When this x is huge compared to the radius of the ring, this can be neglected. Okay, here we have power 3/2, here we have x squared, and here we have another x, and the solution will be like this. Okay, look at the solution. That is, when the ring is so far away that its radius is negligible in comparison to the distance x, as I explained, its field is the same as that a point charge. Okay, look at the electric field. Remember the electric field produced by a point charge. It is given with this expression. Okay, so this equation goes to this expression, the electric field produced by the point charge. So in the book, there are also many other examples related to the electric fields produced by other shapes. Tin rod, metal, or plastic charged sphere. Okay, you can solve this once and you will use the charge density lambda, sigma, or rho, depending on the problem, depending on the shape of the electric field source. Okay, let me continue with the electric field lines. So we have learned electric fields, we have learned electric force, and we will learn now another term, electric field line. Okay, so electric charge, we have learned electric force, we have learned electric field, and now we will talk about electric field lines. Okay, field line. So these two terms are different. Of course, they are related to each other, but they are different terms. So this is the definition of electric field line. Electric field line is an imaginary line or curve whose tangent at any point is the direction of the electric field vector at that point. So here we have electric field line. This is the electric field line, but this is not the electric field. Here at this point, you would like to get the direction of the electric field. This is the direction of the electric field, tangent to this line. Here at this point, point R, you would like to get the direction of the electric field, the direction of the electric field tangent to the electric field line. Okay, so this is the relation between electric field and electric field line. I will show you more examples and you will better understand. So here we have a positive charge and we have field lines from charge to the space. Okay, these are the electric field lines produced by this charge. And now here at this point, I would like to get the direction of the electric field. Electric field is tangent, direction of the electric field is tangent to the electric field line. So then these are the electric field lines. Okay? But here there is something else in the figure. Please carefully look at the figure. What do you see here? At this point, let's say this is the A point and this is the B point here. At A point, I have field line, electric field line like this from the source to the space, and at this point the electric field is in this direction. But look at the amount of the electric field. The amount of electric field at A point is very small. Why? Remember the electric field formula. 1 over 4 pi epsilon 0 cubed over r squared, distance to the source. And here we have unit vector. So this is the distance to the source, RA. And here I have another point, B point. Look at the distance. Distance is RB, very small. If distance is small, then electric field is bigger. Okay, so for this reason here I am showing bigger vector here, okay, because it is a closer point to the source, to the charge. I hope it is clear. Here there is another important information which I have shown with this yellow color. The spacing of field lines gives a general idea of the magnitude of the electric field at each point. So just choose a 1 centimeter area here, okay, and just choose 1 centimeter area here. So within this 1 centimeter area, we have many field lines, or we have 2 field lines, okay, but here we have only 1 field line. So if you far from the source, okay, the magnitude of the electric field decreases. It is also related to this formula, okay? This is the statement. So here we have important information. I have already explained, but I would like to read this one. Notice that in general, the magnitude of the electric field is different at different points on a given field line. A field line is not a curve of constant electric field magnitude. This is very important. So just take this one. Let me use another color. Here I am choosing different points. This is A point, this is B point, this is C point. And I would like to calculate the electric fields here. Here it will be like this. Electric field. Here it will be like this, smaller, and here it is the smallest, okay? So along the same electric field line, we have different electric fields due to the distance relation of electric field. Okay, I hope this information is clear. Then let me continue. So now let's continue with the electric fields line of a dipole. What is dipole? Dipole is 2 equal charges. So they have equal charges in magnitude, but they have opposite signs. This is electric dipole. Here I have negatively charged particle. Here I have positively charged particle. You can consider molecules, atoms, ions, okay? But in magnitude, they have same charge. Okay, this is dipole. And in electric dipoles, we have field lines from positive to the negative, okay? From positive to the negative, from positive to the negative. Because if you take a single positive charge, electric field lines will be like this, from source to the space, right? But if you have a negative charge, as we have discussed before the break, we will have electric field lines from space to the source, okay, if you have a negative charge here. So then if you put them together, if you make a dipole, then we will have this type of electric field lines. Okay, what do you see here? That we have electric field lines from positive side of the dipole to the space and to the negative side. And for this one, we have field lines from positive to the negative or from space to the negative. Then this is showing us the electric field lines of electric dipole. Again, I have already shown you, I have already discussed this one, but I would like to repeat this one. The magnitude of the electric field is different at different points on a given field line. So just consider this field line here. Let me use another color again. Let me show you this blue color. This is the electric field line. And I would like to calculate the electric field at this point. I would like to calculate electric field at this point. I would like to calculate electric field at this point, and I would like to calculate electric field at this point. So here, the electric field direction is tangent to the field line. Here, electric field direction is tangent to the field line. Electric field direction is tangent to the field line, and electric field direction tangent to this line. But what I am doing here, that I am showing the magnitudes of the vectors different for each point. Why? Because along the field line, depending on the position of the point, the magnitude of the electric field is different. Why? Again, it is related to the formula of the electric field. Look at the formula of the electric field and remember the superposition of field lines. So, electric field formula, everything is logic, okay? Q over R square, right? This is the electric field formula. And here I am choosing a point. So here I have electric field component, let's say due to this positive charge in this direction. And here I have another electric field component in this direction, smaller one because it is huge distance, okay? Then in total I have sum of them, okay? This is the vector addition. So this is superposition of two contributions. If I choose here another part, it will be tangent to the field line. So look at this one. You can do like this. Okay, then this is the superposition of two electric field vectors due to two charges. Okay, so depending on the point, you can calculate electric field, and it will be different for electric fields on a single electric field line. I hope this information is also clear. Then let me continue. Here we have discussed electric dipole, negative charge here and positive charge here. But what about two positive charges? Or what about two negative charges? Then we will have different electric field lines. Here I have a positive charge. Here I have another positive charge, and field lines from charge to the space. Here on the left side, field lines charge from the space, and electric field at any point on the line is tangent to these lines. Okay, if I choose a point here, electric field is tangent to the field line. But here, at any point, the electric field has a unique direction. So each field line here has a unique direction. So field lines never intersect. Okay? So this information is important. Now, let me show you one example. This is from the book, electric field lines produced by two opposite charges, or dipole, electric dipole, okay? The pattern is formed by grass seeds floating in mineral oil. The charges are on two wires whose tips are inserted into the oil. Let's consider that here we have a tank. It is filled with oil, okay? And this is the surface of the oil. And you put grass seeds, okay? Many grass seeds. And then you put two wires into this oil. Okay. And then just consider you use a battery here. Let's say this is the positive pole of the battery. And this is the negative pole of the battery. Okay, then here we have negative, here we have positive. Okay, then here we have a charge source. Okay, so we will have field lines like this. Look at this one. We will have field lines like this. Okay, then grass seeds will be aligned like this. These are the grass seeds. This is the picture of the grass seeds in oil. Why we have this type of pattern? Because grass seeds are neutral, okay? But I told you in the first part of this chapter that due to the polarization, neutral particles, neutral objects can also be aligned under the electric field, okay? So just consider you have a grass seed. This is the shape of the grass seed that's considered, and it is neutral. The total net charge is 0, okay? Q is 0. But within the grass seed, there are particles, molecules, let's say, okay? And if I put this seed here, just consider I put this seed here. So here I have positive side, here I have negative side. So within the seed, electrons will be attracted by this positive part of the wire, and here I will have positive side. Then with electric polarization, I can produce this type of structure in terms of electricity within the grass seed. Then it will be like this. Then it will be aligned along the electric field line. Here I have electric field lines. So each grass seed will be aligned along the electric field lines. Okay, due to the polarization, which I have explained during the last lecture. Do you have any question here? Okay, then let me continue with the water molecule. It is an electric dipole. At the beginning of this chapter, during the last lecture, I have explained that water is very good solvent and very important material for our life, okay? Without water, our body cannot dissolve the biological molecules in our body, okay? So how water can do that? It comes from its property. Water is an electric dipole. So you know water is given with this formula, H2 oxygen, okay? So hydrogen is positively charged, but oxygen is negatively charged, okay? In total, I have two positively charged hydrogen, and I have one negatively charged oxygen. In total, it has 0 net charge, okay? But due to the chemical bonding of hydrogen and oxygen atoms in water molecule, we have this type of shape of the water molecule. What do you see here? Positively charged hydrogen atoms are located here, and negatively charged oxygen atom is located here. Oxygen is negatively charged and hydrogen atoms are positively charged. So due to the chemical bonding, due to this arrangement of the atoms in water molecule, we have positive charges located here, and we have negative charge located here. Then the result is a net negative charge on the oxygen end of the molecule and net positive charge on the hydrogen end of the molecule. Then it forms an electric dipole. Okay, here I have positive charge, here I have negative charge, and it is electric dipole. Okay, so in total. And it has certain electric dipole moment from negative to positive. Okay, here again we use P symbol. In the previous lectures in physics 1, P symbol used for different terms, but here we have to use again the P symbol for the electric dipole moment. Please don't confuse with the previous ones. So this is the direction of the electric dipole moment P from negative to positive. Okay, so this seeds has electric dipole moment, and then they are aligned under electric field along the electric field line. So now let me continue with the property of the water. As we have discussed, water is very good solvent. Okay, so the water can solve the materials and it can keep the solution more or less constant for a long time. Okay, so then we can use aqueous solutions. So how it could be possible? Just consider that here we have a cup of water. Okay, here we have a water, and I add some salt into the water. Okay, so what is water? Water is H2 oxygen. And as I told you that hydrogen atoms are located here, oxygen is located here, then here we have positive charge, here we have negative charge, and then we have this type of dipole moment, electric dipole moment of the water. What about the salt? Salt is sodium chloride, right? And sodium is positively charged and chloride is negatively charged. When sodium and chloride ions salt within the water, this positively charged sodium ions will come negative side of the water. This negatively charged chloride ions will come to the positive side of the water. Then we can keep the ions in solution. Okay, so when dissolved in water, salt dissociates into a positive sodium ion and negative chlorine ion, which tend to be attracted to the negative and positive ends of water molecules. Then this holds the ions in solution. But if water wouldn't have this property, what about the life? What about the solvents? What about the chemistry? What about the life for our body? If water molecules were not electric dipoles, if this type of arrangement of the molecules in water wouldn't be possible, then aqueous solutions would be impossible. Okay, so due to this property, water can collect negative ions in this side and it can collect positive ions in this side, and then it holds the ions in solution. Here in the picture on the right side, you can see different aqueous solutions within the water, and you can keep them for a long time. Okay, this is electric dipole property of the water molecule. And water is very important for chemistry, for physics, and also for our life, and for also many applications. And it can do that with its electrical property, okay, because it is electric dipole. I hope it is clear. Then let me continue with the force and torque on a dipole. Then I will talk about the energy of a dipole, okay? So this information, force and torque, you already learned what is torque during the physics 1 in the last semester, okay? So I will use the same idea and you will easily understand, you will easily remember. I will also explain the potential energy due to the electric fields, due to the electric force, okay? So this information also you already know from the physics 1. I just repeat them in a short time and you will remember easily. So now let's have a look this picture on the right side. Here we have an electric field source. Just consider that here I have a plate. This is positively charged. And here I have another plate. This is negatively charged. Okay. And they have certain distance in between, d, and we have uniform electric field between these plates. This information is important. If you can produce good parallel plates, you can get uniform electric field. So the magnitude and direction of the electric field is same as the electric field here and also here, okay? So in every part of the system within these parallel plates, electric field is same in terms of magnitude and direction. And here, between the plates, we have uniform electric field. I hope this is clear. Then I will explain the mechanism. So I have parallel plates and I produce this electric field shown by the red color, let's say. This is the electric field direction from this side to this side. Then I put here an electric dipole. This is positive side of the electric dipole. This is negative side of the electric dipole. And this is the electric dipole moment of the dipole, okay? This is the distance between the charges in the electric dipole. So due to this electric field, there is a force acting on this positive side of the dipole. It is along the positive x-axis, let's say, okay? And here we have negative charge, and there is another force which is given with this expression. Since the charge is negative, the direction of the force is different. Okay, here we have positive charge, here we have negative charge, then the direction of the force is opposite here to the electric field. Okay, now what about the net force acting on this electric dipole? Here we have force given with this expression. Here we have force given with this expression. Since they are same in magnitude, the net force acting on the system is 0. But what about the net torque acting on the system? It is different from 0. Okay, under electric field, this electric dipole will be rotated. Okay, what about the direction of the rotation? You know this information from the physics 1. Okay, so here we have a net torque. Now we can calculate the net torque. So what about the torque? Torque is given with force times lever arm, right? You remember from the physics 1, force times lever arm. What is the force here? Force is given with Q times E. What about the lever arm? The distance to the rotation axis. Okay, this lever arm is given with d½ sinus phi. And here we have lever arm for this charge, and it is also given with d½ sinus phi, right? Then I have two torques, QE for the positive one, d½ sinus phi. This is the torque for the positive charge, and there is another torque for the negative charge, QE d½ sinus phi. What about the direction of the torque? It is same for the both cases, right? Then What about the net torque acting on this system? The net torque is this one. This plus this one. Then here I have d half. Then here I have d. QED sinus phi. Okay, this is the net torque, magnitude of net torque. And what about the direction of the torque? Direction of the torque is into the page. Okay, and the direction of the rotation is clockwise. Okay, I hope it is clear. Then here I have Q times D. You see, what is Q times D? Q times D is given with electric dipole moment P, magnitude of electric dipole moment. Okay, then I can write this expression like this: torque P times E sinus phi, right? Instead of Q times D, I just use P, okay? What about the unit of this electric dipole moment? It is charge times distance, Coulomb times meter, Coulomb meter, okay? And what about the magnitude of electric dipole moment of a water molecule? It is given with this one. 6.13 times 10 to minus 30 Coulomb meter. So what is the shape of the water molecule? Roughly, hydrogen atoms and oxygen is here, and these are positively charged, and this is negatively charged, and we have dipole like this. Okay, this is the distance between negative and positive charges, and charge is also known. Then you can calculate the electric dipole moment of the water molecule. So as I told you here, the symbol P has multiple meanings within this book, also in other physics books. Don't confuse dipole moment with momentum or pressure. For the momentum in the physics one, we have also used P symbol. For the pressure, we have also used P symbol. And here for the electric dipole moment, again, we are using P symbol. But the context usually makes it clear what we mean. You have to be careful. Okay, now let me continue with this one. So then here I have PE sinus phi. I have written this one here. Okay, so what do you see here? This is the vector product, right? I can write this expression in this form because here I have sinus phi, P vector product E. Okay, this is the electric field, this is the electric dipole moment, and this is the vector torque on an electric dipole. So here there is useful information. Please listen carefully. I have also this type of statement and explanation. These are very important for the forthcoming chapters in order to understand the mechanism of the topic, okay? So then you don't need to keep something in your mind. If you understand the mechanism behind the topic, behind the equation, then you can easily understand. So now let's talk about the torque condition. Here we have torque equation, P E sinus phi. So this is the direction of the P. What is P? Magnitude of electric dipole moment. This is the magnitude of electric field. And this is the sinus of the angle in between. So here, what about the direction of the electric field? This is the direction of the electric field. And this is the direction of the P, electric dipole moment, right? And this is the angle in between, phi. Then we have this torque. So what about the maximum and minimum torque? If phi is 0 degree, or if phi is 180 degrees, just consider these conditions. Phi is 0 degree. What is the meaning of that? this electric field and electric dipole are in the same direction. What is the meaning of this? Phi is 180 degrees. Electric field is in this direction and dipole is in this direction. Okay, they are opposite to each other. You can also consider other conditions. Okay, so if you put 0 here in the sinus phi, or if you put 180 degrees here, then the torque will be 0, right? In that conditions, torque will be 0 and there will be equilibrium. But this condition is stable equilibrium and this condition is unstable equilibrium. We have learned stable equilibrium, unstable equilibrium in the potential energy part of the physics 1. During the last semester, you have learned stable and unstable equilibriums. So what is the meaning of that? You have electric field in this direction and you have electric dipole moment in the same direction. So it is happy to stay parallel to each other because the net torque acting on the system in this condition is 0 due to this expression. Okay, because they are parallel to each other. When they are anti-parallel to each other, again, the net torque is 0 acting on the system. But this is unstable condition. If this P polarization is slightly deviated from the anti-parallel condition, then there will be torque acting on the system. And this torque will try to align the electric dipole along the electric field. Okay? And what about the maximum torque if electric field direction is like this? If electric dipole moment is like this, then the angle is 90 degrees. Then what about the torque? This one, sinus 90. Maximum condition, okay? And here we will have maximum torque acting on this one. Then it will try to align the electric dipole along the electric field. So these are the different conditions depending on the angle between electric dipole moment and electric field. Now let me continue with the potential energy. During the physics 1, again, we have discussed the potential energy, and potential energy for this condition is given with P times E times cosine phi. Okay, torque is given with sinus phi and positive number here, but here we have negative PE cosine phi. Okay, you can also write this expression like this in scalar product. Okay, then potential energy for an electric dipole in an electric field with this one. What about the meaning of this one? It is very nice. Please keep this information also in your mind. Very easy to understand. So here I have potential energy formula and it depends on the phi angle. P, E, cosine phi. Now just consider different condition. Phi is 0. What is the meaning of 0 phi? Then electric field is in this direction and electric dipole moment is also in the same direction. Then what about the potential energy? Minus P E. Cosine 0 is 1. Okay. And what about the unparalleled condition? This one. E P. And now, what about the potential energy? Cosine 180 is minus 1. Here I have another minus, then here I will have positive PE. I will explain the meanings of these solutions. Then, what about 90 degrees? Potential energy is 0 because cosine 90 is 0, right? Cosine 90 is 0. This term will be 0. So now what about the meanings of these potential energies? Just consider that this is the potential energy depending on the phi, and this is 0. This is negative PE, and this is positive PE. Which one is minimum? This is minimum, this is maximum. So we have learned that in physics 1, systems prefer minimum energy, okay? If electric field and electric dipole are along the same direction, the system electric dipole would like to be along the electric field because in that condition energy is minimum. And this is unstable equilibrium. Torque is 0, but potential energy is maximum. Remember the potential energy graphs for unstable and stable equilibriums. You can easily understand. And here we have an intermediate region, and this is the minimum energy condition. So with this one, I think I have finished the force and torque and also the potential energy of an electric dipole. Now I will continue with the field of an electric dipole. What about the field of an electric dipole? I have already shown you in this figure in the previous transparency. I am using the same figure here. Here we have negative charge, here we have positive charge, okay? And we have field lines of an electric dipole. At each point in the pattern, the total electric field is the vector sum of all the fields from the individual charges. Vector sum of the fields from the individual charges. I have already done this one. So you would like to calculate the electric field in this direction. The direction will be tangent to the field line. But what about the magnitude? You have to calculate this component. Then you have to calculate this component. And then superposition of electric field vectors. Then you can calculate the direction and magnitude of the electric fields produced by each charge of the electric dipole at this P point, for example. So now I have two transparencies. First of all, I will give you the bio application, then I'll have one example, then I will finish my lecture. Okay, bio application, a fish with an electric dipole moment. I have explained the electric field detection mechanism of sharks. Here we have another type of fish which produces electric field lines around itself. This explains this one. Unlike the tiger shark, which we have seen in the previous transparencies, which senses the electric fields produced by its prey, the African knife fish, this one, this is the African knife fish. So this is nocturnal and has poor vision. The African knife fish hunts other fish by generating its own electric field. It can make its tail negatively charged relative to its head. So just consider that this is this fish. So what it says, it can generate its own electric field. It can make its tail negatively charged relative to its head. So it can collect negative charges around the tail, and then it becomes positively charged. Then this fish has electric dipole. Then we have field lines from positive to the negative. Okay. Field lines from positive to the negative around the fish. Then, when a smaller fish ventures into the field, its body alters the field pattern and alerts this fish that a meal is present. Just consider that another small fish is coming and enters into this area. Whenever this fish enters this area, it disturbs these field lines, okay? Then this fish can understand that meal is ready, okay? So this is the working principle of electric dipole moment in a fish. Let me finish this lecture with this last example. Actually, there are also many other examples within the book. Please, after the lecture, repeat all these examples and also check the examples which is not discussed within this lecture. So now, field of an electric dipole. An electric dipole is centered at the origin. Here we have an electric dipole. This is the positive charge, positive Q. Here we have negative Q. This is the origin. This is the x-axis. This is the y-axis. And the distance between two charges is given with d. Okay, here we have electric dipole. Derive an approximate expression for the electric field at a point P on the y-axis for which y is much larger than d. So here we have P point, okay? And what is the electric field due to the dipole here? Here we have positive charge and electric field direction will be like this at this point due to the positive charge. And here we have negative Q, negative charge, and at this point, this negative charge will produce an opposite electric field from this point to the negative charge, okay? And then the net electric field can be calculated by calculating these individual electric fields produced by the individual charges in the electric dipole. What about the magnitude of this electric field produced by positive charge? What about the distance? This is the positive charge and P point. Look at the distance. This is the P point and negative charge. Look at the distance. So you can easily expect that the electric field due to the positive charge will be larger than the electric field due to the negative charge because there's a distance difference in between, okay? And this distance is given with this expression for the negative charge, y plus d half, for the positive charge, y minus d half, okay? Then by using the expression for the electric field, what was the expression for the electric field? This one, let me draw here. So it will be like this, 1 over 4 pi epsilon 0 q over r square, okay? You will write r for the positive charge and you will write r for the negative charge, and we have positive q and negative q. Then finally you can get this expression. You see, this is due to the positive charge, this is due to the negative charge. Total net electric field at this P point. Then you can rearrange this one, you can rearrange this one, and if you use this formula 1 over x power n, this is the binomial expansion, okay? You can write this one approximately 1 plus nx plus n times n minus x squared over 2, and it goes, okay? It is only valid if x is smaller than 1. Here, what is x? Here we have n minus 2, this power, n is minus 2 here, okay? And here, instead of x, here we have minus d over 2y. Here we have plus d over 2y instead of x. And if you open this one, if you use this binomial expansion, then you can rearrange this term here. You can rearrange this term here by using the binomial expansion. Then finally, just put them here in the equation. Then you can get this expression. Here we have q times d. Q is already here, 4 pi epsilon 0 y square. And from this expression and this expression, another y will come. Here we have y cube, okay, y power 3. And here we have d, also comes from this binomial expansion. And what was q times d? Q times d is p, electric dipole moment. Then you can calculate electric field in this form. Okay, so with this example, I finished this lecture. At the end of the chapter, there are many examples and many problems. Please try to solve all of them. And then on Saturday at 11, you will have a quiz, okay? The questions will be very similar to the problems at the end of the chapter. And I strongly suggest you to solve more or less all problems at the end of the chapter.